Hey everyone, welcome back to another explainer. Today, we're diving into something that's absolutely crucial to both the healthcare and tech spaces right now. We're breaking down a fantastic GitHub repository by Ramayanam Saikiran. It's called the Heart Disease Prediction System, and let me tell you, this is a complete end-to-end machine learning application. But here's the kicker. It doesn't just stop at predicting a diagnosis. Nope. It takes raw clinical data, processes it, trains the models, and actually pushes the whole shebang to a fully deployed application.
So, let's dive right in. The big question at the heart of this project, and honestly what makes it so unique, is this. Can we predict heart disease while also explaining the financial risk? Usually machine learning models in healthcare just stop at the clinical diagnosis. But this project brilliantly bridges that gap between medical prediction and real-world business impact. It's not just asking, will this patient get sick? It goes a step further and asks, what is the tangible financial impact of that outcome? It is a total game changer for how we look at applied AI. To see exactly how Ramayanam Saikiran pulled this off, here is our roadmap for today's explainer. We're going to cover 1. The clinical data foundation, 2. Building the ML pipeline, 3. Training the predictive models, 4. Explaining predictions with SHAP, 5. Financial impact analysis, and finally, 6. Deployment and interactive dashboard. Let's get into it. All right, section 1, the clinical data foundation. Because, well, every great predictive engine needs raw material to actually power it.
303. That's it. That is the exact number of patient records serving as the bedrock for this entire project. You really don't always need millions of data points to build something that's highly effective and educational. 303 records is a perfectly specific, manageable data set. It's great because it actually lets us see very clearly how every single processing step affects the final outcome.
Sourced from the highly respected UCI heart disease dataset, we're looking at 14 distinct clinical features. Think of things like a patient's blood pressure, their cholesterol levels, or their age. But the absolutely crucial detail is that target variable at the bottom. This is what we call a binary classification problem. Basically, a 0 means no heart disease and a 1 means heart disease. Everything we're building from this point forward is designed to accurately predict that 1 or that 0 purely based on those 14 features.
Which brings us to section 2, building the ML pipeline. This is where we shift gears from just gathering raw data to actually constructing a highly structured processing machine.
Now, the repository actually details 9 comprehensive steps in its machine learning pipeline, but we've boiled them down into the 6 most critical logical phases. Because, let's be real, you can't just throw raw data at an algorithm and expect a shiny dashboard to pop out the other side. First, the data has to be cleaned. Then, any missing values are handled. Next up is feature engineering. That's where we create new, more useful data points from the ones we already have. Then we explore the data, train and tune the models, and finally, we deploy. It's a beautifully structured workflow.
I want to zoom in on step 2 for a second, because it uses a pretty vital technique. It's called MICE. That stands for Multiple Imputation by Chained Equations. See, in the real world, medical records are almost never perfect, right? They have missing values. MICE is an imputation technique that intelligently fills in those gaps in the clinical data before we even touch feature engineering. Instead of just throwing away incomplete patient records, which would totally waste our precious 303 data points, MICE robustly predicts what those missing values actually should be, so it completely preserves the integrity of our dataset.
Okay, so now our data is clean and complete. Let's move to section 3, training the predictive models. This is where the processed data finally meets the algorithms.
What's cool here is that the project doesn't just rely on one single approach. It actually pits 2 very different heavyweights against each other. On one side, we've got the random forest classifier, which is this traditional, highly robust, tree-based ensemble method. And on the other side, we have the multi-layer perceptron, or MLP, which is a foundational neural network model. Testing a structured tree-based model against a neural network is just an excellent way to see which architecture fundamentally understands the clinical data better. And of course, the project uses Grid Search CV to perfectly tune the hyperparameters for both of them.
But how do we actually know which model wins? Well, in healthcare, just being accurate isn't enough. Think about it. If a model predicts that nobody has a disease, it might technically have high accuracy if that disease is super rare, but it would be completely useless in a clinic. That's exactly why this pipeline also measures precision, recall, and the F1 score. Recall, for instance, tells us how many of the actual heart disease cases the model successfully caught. For a medical tool, missing a diagnosis is, well, critical. So these comprehensive metrics really ensure true clinical reliability.
This naturally brings us to Section 4, Explaining Predictions with SHAP. This is arguably the most crucial conceptual pivot in our entire explainer.
We are officially moving away from the dreaded black box of machine learning. SHAP, which stands for Shapley Additive Explanations, is a framework used to demystify these complex models. It literally calculates the exact contribution of each clinical feature to a specific prediction. You can kind of think of SHAP like a flashlight. It shines a light straight into the algorithm and reveals exactly why the model made the decision it did.
And SHAP is applied in this project on 3 distinct levels. First, there's global feature importance. That tells us which features, like say cholesterol or age, matter the most across all 303 patients. Second, we have individual patient predictions. So if John Doe is predicted to have heart disease, SHAP tells us why John Doe specifically got that result. And third, feature contribution analysis. This breaks down the why behind every single medical prediction, making the AI completely transparent to the doctor or the end user. It's a real game changer.
Now, let's look at Section 5, Financial Impact Analysis, because this is where the project builds into something completely unexpected.
This is the unique business value proposition that elevates this repository way beyond your standard academic examples. Beyond just clinical accuracy, this model actively estimates the financial risk associated with its predictions. It doesn't just diagnose the illness. It takes those medical probabilities and translates them into actionable financial risk metrics. Whether you're an insurance provider trying to assess risk or a healthcare network needing to allocate resources, this tool speaks the language of both medicine and finance simultaneously. Pretty amazing, right?
Finally, we arrive at Section 6, Deployment and Interactive Dashboard, because all of this complex data science really needs a home.
I mean, what good is a model if no one can actually use it? The author built this highly user-friendly interface where you can easily just input patient data. Instantly, you get the heart disease prediction probability. And right next to that, you see those SHAP explanations telling you exactly why. And finally, the financial risk estimation pops up. It's this beautiful, seamless integration of predictions, transparency, and financial analysis, all sitting in one place.
And the technology stack powering this dashboard? It's incredibly modern and accessible. The whole thing is built entirely with Python and Streamlit, which is just fantastic for rapidly turning data scripts into shareable web apps. Even better, the entire environment is deployed via Docker. By combining Pandas, Scikit-learn, Streamlit, and Docker, this really complex pipeline is neatly packaged up into an easily deployable, scalable blueprint that literally anyone can run on their own machine. So the really crucial takeaway from this repository is just how interconnected these disciplines have become. We've gone from 303 lines of raw data, handled the missing values with mice, trained powerful models, illuminated them with SHAP, and then tied it all to real-world financial realities in a Streamlit dashboard, which leaves us with this final thought. As AI continues to unlock both our medical and financial futures, are you ready to take these concepts and build the next predictive lifeline? Thanks so much for joining me for this explainer. Keep learning, and I'll see you in the next one.